Hello and welcome to Chemspec Digital. I have the pleasure to introduce the next presentation in the RSC Symposium. But before I do want to let you all know that we are recording this presentation to be able to be viewed on demand later. Attendees are invited to write questions into the chat function from where we will read them out at a later date. And now, without further ado, I will hand over to Professor Sean-Wei Ni of NiTech Solutions, who will be presenting What is the Fuss About Continuous Crystallization?
Thank you, Christina. And yes, my name is Sean-Wei Ni, and today is going to really mainly focus on continuous crystallization. And NiTech Solutions is based in Edinburgh, Scotland. And the structure of the talk is really, we need to understand why we're doing continuous and what are the problems. And then I just go through what is our solutions. I have a lot of solutions. I will focus on our solutions. I show you some applications. And also I have a short video as well at the end of this. And because I just test the system and I need to stop my presentation before I can show you the video at the end. Then at the end, the takeaway messages. So in the world we live in today, 80% of pharmaceuticals and 60% of fine specialty chemicals, explosives, suntan cream, so forth, and 30% of food are manufactured in crystalline form. This is why crystallization is very important, a branch of chemical engineering. So all those things you see in the previous slides, or either the functionality or the bioavailability, so forth, are represented, really expressed by crystal size, shape, morphology, and purity. And those are controlled by two set of parameters. And I named them environmental, which is the parameters you can change, you can manipulate, and the scientific parameters you have to derive and to either derive or model, so forth. So what are the problems? So this we have to go back to very basic of crystallization, the thermodynamics. So we have vertical, if you can see my arrow, and we have vertical axis concentration and a horizontal axis temperature. So this is your solubility curve. And we also have a super solubility. This and within between these two is metastable zones. So ideal crystallization pathway is within these two, within the metastable zones. So you get a very nice crystal, so forth. So this is our boundary to live with. This boundary here to live with, metastable zones. However, this boundary, the super solubility, in fact, changes depends on so many parameters, temperature profile, history, solution history, impurity, etc., etc. Those actually changes with size of crystallizer. So this is the key problem here, because whenever you learned in the lab scale, once you change the scale, and this changes, so you cannot apply what you learned to the next stage. And in addition, and once you scale up in the batch-wise, once you scale up in batch-wise from 1 liter to 1 cubic meter, 10 cubic meter, and the area, the specific surface area for heat transfer reduces. You can hear reduced by 100 times. That means it takes much longer to heat and cool a vessel. So we all know that this is a fact, century-old facts. Mixing gets worse and with increasing scale. So if we have mixing ingredients in crystallizer, and this will cause concentration gradient. For example, here I have two curves here. And if I'm on this curve, I'm good because I'm still within the metastable zones. But if on this curve, I'm outside. The trouble is in the large batch, you don't know when you're in, when you're out. And also this is a similar things, and mixing gradient can lead to concentration gradients, and this temperature gradients also affect kinetic. So what is this? Is really the outcome we normally heard about is inconsistent morphology, wide size distribution. And once you, for example, if you see my arrow, if you go over the metastable zone waves, you get those crystals, very small crystals that don't grow. And once within metastable zone waves, crystal grows. So once you do the filtration, those small crystals will block the folds of large ones, and the filtration time is significantly long in industrial batch. So what we need is really an environment, flow mechanics environment, which is consistent for crystallization. And in here is really, this is nothing we can do about. We need to achieve plug flow because this gives you consistent environment. And you cannot achieve plug flow in batch reactor. And this is why you have to flow. You have to do continuous operation. This is why all the branch of flow chemistries, it means we are needed to change the environment for reaction, crystallization, so forth. And so now the word's plug flow has floating around many times, and in medium, so forth. So what is plug flow? In order to understand what is plug flow, you need to understand, starting with laminar flow, then turbulent flow. So in here, laminar flow have an income flow, and it will have the typical parabolic flow front. So the lighter phases will have the same velocity as income flow, and heavy phases will have much less velocity. So you have a different resonance time. The lighter phase goes first, heavy goes last. If the flow rate increases to such an extent that the Reynolds number is over 2000, and some book says 2500, and 80% of the flow is same as income flow, but you have this laminar sublayer where the energy dissipation, so forth, taking place. So the plug flow means that everything goes out just like everything. So there's no overtaking in the flow direction, but perfect mixing in this direction. That's called radial direction. And all elements, this light phase, heavy phase go out just like same time. So if you chop out the tube and every cross section and give you same things, that's like a plug. This is why the name of plug flow comes from. So now how do you achieve plug flow? This is really, I've been talking about it many times now. They only have two ways. One is have a tank in series. And this is many hundred years ago, people knows how to use this. The trouble is to achieve plug flow, the number of tanks got to approach infinity. So this is really impossible. And every time you increase a tank, that means you have an inventory and cost, so forth. And also because the number is always a definite, therefore it's far from plug flow. And the second method is to use flow. As we say, if you achieve turbulent flow, you are closing to achieve plug flow. So in this case, either you have a tube without inserts, just a smooth tube, or you have some inserts like this shows. Yeah, so so-called static mixer loop reactors. So based on this methodology, the mixing mechanism is based on the net flow element. So they need a higher flow rate and therefore very long reactors. And the major drawback is the reaction time. You can only accommodate a very short reaction time. So what is our solution? So our solution is really a symmetry buffer here. So we have, if you can follow my arrow, I have an oscillation here, and the buffer, the tube here is glass tubes, and the bands are all jacketed, and inside have buffers, a pair of buffers. All the buffers cross in the glass tube. So each tube can be controlled temperature-wise, can control independently, or it can connect all things together as one. So if it's one, you can do reaction. For crystallization, I will show you later, we need to break the jacket into different zones. And if we put conductive probes in different locations in the hair and inject tracer down here, and we'll get this the resonance time distribution, RTD. This is really a fingerprint of good plug flow. The definition of plug flow is the area on the curve equals to 1, or the width equal to 0. So you can see here, nobody can achieve true plug flow. You can get close. And for chemical engineer and the learned use tank in series model or actual dispersion model to evaluate how good, how bad your reactor is. So in here, for example, if you're in tank in series model, the number of tanks for this system is 550 over 60 minutes. This is where the number of tanks, the higher, you get a better plug flow. And the actual dispersion coefficient really describe how wide is this curve here. If you see my arrow here, so normally you can reach decimal 2 point, and here you can reach decimal 3 and 4 point. So other things is the mixing is one thing. It's called consistent environment. Also, you have to have ability to put heat in, take it out much faster. So you can see, I showed you previously, if you scale up in batch wise, the specific area decrease. But if you use tubular wise, actually they're just like your lab scale equipment. This is why you can use different type and cooling rate, so forth, that cannot be used in batch crystallization. So here is the example. Just say, how does it work? What is the operating principle of continuous? Here, just a typical example here is API. The trouble for this one is the metastable zone width. Is this width here is only 3 degrees. If you use a 1 ton tank, for example, the temperature change within the tank and will be exceeded the 3 degrees. So that means sometimes it will go out, sometimes go in. So this compound is starting with 50 degrees, we'll start some down here. We want to finish at 10 degrees. So that is your yield here for 10 degrees. And this is your solubility curve, saturation here at 40 degrees. So we want to add C's at 30 degrees. Because we don't have any heat mass transfer constraint, we can do very simple calculation here. So from where's my arrow here? From 50 to 40 degrees here, and in here, you can cool as fast as you can, because this part is unsaturated region, has no effects on crystal properties. So in here we choose 10 degrees, you can choose 5, you can choose 7, after your choice. And from once you come into the metastable zone width, you go cooling slower, you cooling, you get a bigger crystal. So you can choose 1 degree here per minute. You can choose 0.75, 0.5, after you wish, depends on what you want. And so we have a 31 minutes, that's our time. And also because the lab scale crystallizer here is 20 meters long, so we have a velocity, we have a flow rate. You can see here the flow rate is around about 52 milliliter per minute, and the Reynolds number is about 9 milli. So how do we do this? So initially we have a solvent tank. So this feed tank is switched off. The solvent tank is going to pump this in, pump some in, and the circulating come back to the solvent tank. So you have the circulation here going. By doing this, we have 2 purposes. One is to get rid of some bubbles and in the system, so it's bubble free. And second purpose is to set up your temperature zones. You break up your jacket and connect few tubes as a group. That's your zone. So we have a zone here, 50 to 40, and 40 to 30, 30 to 20, and 20 to 10. And once the temperature set up, now your solvent tank is switched off, your feed tank is switched on, and come in. So you run about, if you talk about, it's run about 1 mils per second, just less than 1 mil per second of fluids coming through, goes through different temperature zones, and then we seed at 39 degrees. So we now, if talk about this is science, and the science now is combined, it's connected with operation. So you know exactly where you seed, and this, you can run this for many hours. So we run for 8 hours, and this is published in the Handbook of Continuous Crystallization. So this is how to operate. This is just how to operate. I'm quite, and now I just show you some applications. So first one is cooling crystallization. Cooling crystallization. This is the AstraZeneca compound, Sericon. And obviously this is quite old literature. Yeah, so it's published in 2009, the work came out by AstraZeneca. So the key things here is just crystallization time in continuous crystallizer is 12 minutes compared with a batch time of 9 hours 40 minutes. You get a uniform size distribution, and so majority of content are published there. Then we can do anti-solvent. I can do anti-solvent crystallization. Here, anti-solvent crystallization here, and here we have a solvent is mixture of ethanol, water, and toluene. Anti-solvent is water. So if you follow my arrow, the water anti-solvent come in first and flows right to left, and then solvent come in here. So that once meet, nucleation taking place, and then it grows, and you have some probes here. And once the grows enough, because in this application you want to have a large agglomerate, so you add, or my arrow here, you add the binder here. The binder here is toluene, so you can add the binder here, and then everything just flows out and goes out. So yeah, this again, you have temperature zones. You can achieve this type of agglomerate. So here, this is again published paper in 2017, and using this type of crystallizer, and you get improvement in the size and the structure of a agglomerate. And you can do combination of cooling plus anti-solvent. This is work done in CMARC. This is one of the Lavata's API. So this is doing two platforms. One is this COBC platform, continuous solid-state buffer crystallizer, and also this multi-stirred, multi-separate and crystallization system. So both have 3 zones. This is temperature zones, yes, and somehow I'm going to move this to the other side. I can use my arrow. So they have temperature zones from 40 to 30, 30 to 20, 20 to 10. So here, this is set up, the same zones are set up in the same for 2 systems. And so this is the finding. They compare the particle size distribution, span, and flowability, yield, and also impurity and partition coefficient. So you can just say this is 2 different systems. You can, if you compare the size, slightly bigger than here, then probably the last two rows are quite key sort of parameters. Yield here is higher, and also the partition coefficient is slightly higher than this. And the higher partition, that means the rejection of impurity is higher. And you can also do reactive crystallization. That means you do reaction, then finish and straight away in crystallization. So in this case, it's paracetamol. And so we have 2 components. So the red bit, if you see all the red bit here is reaction section. Temperature is 80 degrees. Then the purple bit is cooling section number 1. The green bit is cooling section number 2. So we can sample out here, sample 1, 2, and end. So remember the sample location, because the next slide will show you some data is from there. And then we have a camera, so you can see here, this is a process images probes. You can see what's going on inside. So what happens initially, we have this 4-aminophenol and pump into here and goes this way. Then the acetic anhydride come in. So 2 A and B meet, reaction taking place. This is just short, this is still this quite a long length. The total length is about 30 meters long. And then, so during the reaction, we have to understand what from this point, what supersaturation we need to have. Therefore, we make up a solution here to meet the concentration so that we generate the right supersaturation there, and then we start cooling. This is zone 1 and zone 2, so forth, like that. So if you see here, the sample from this is inside crystallizer. This is from the solute concentration, and the concentration at the first point is quite high. You can see here, and gradually because crystal comes out, concentration decrease in the sample point 2 and further decrease in sample point 3. So if you know this, and then you can work out the consumption rate of supersaturation, because the solute just come out of solution. You can work out like that, or consumption rate. of supersaturation. And this graph here shows, where's my arrow here, shows the size. So sample 2 and sample 3, because you know the distance, and you can work out the local growth rate. So local growth rate. Again, this is published information. This is polymorph. One is formed with very high purity of crystal. 20 minutes. That's good. So, and all people want to use tubular reactors, crystallizers, always think, oh, this incrustation. What happened to incrustation? Yes, and we have learned a lot from incrustation. We did have a lot of incrustation in the past. The reason, we also know the reason, the solution for incrustation. So I can largely summarize 4 categories. Number 1 is when the metastable zone width is crossed, and you get the spontaneous nucleation, because once you have a spontaneous nucleation, the size is very small, but the number initially is low, and this is why causing problem on incrustation. So the solution is got to use seeds. As I showed you before, previous slides before, we use seeds, we can run it there smoothly. And another thing is, once you seeds, seeding itself looks simple, but they have some science within. And you have to have a right combination of the size and the mass. So I'll actually explain more next slides on how to do this. And another thing is, once you set a temperature zone, sometimes you don't have enough chiller, one missing chiller, so the temperature zone is too steep. That means from maybe 40, you just reduce to 20 straight away, have 30-degree decrease. That means if you look at this graph, if you cross here again, that's the incrustation. So normally we wanted to ensure smooth temperature change. So each zones, they maybe have a small degree change, that's okay, but it has to be smooth change. And another thing is the oscillation is insufficient. It's in particle settles, and then that's what built up, causing incrustation. So here you have to, once we know what crystal size we have, so this velocity is terminal velocity of particles. What is terminal velocity of particles, of largest particles? So the combined velocity, which is the velocity of oscillation plus velocity of net flow, together it got to be greater than that. So you don't have a settlement. This is why increase oscillation amplitude, and it helps as well. And so in the seeding, how do you do this? Really, this is just a traffic map to show you and how do you do seeding. So vertical axis here is the product size. Horizontal axis here is seed loading. So if you use the right combination, and you are in the green zone, and this incrustation free, you can run it as many times and many hours as you wish. But if you're in the wrong zones, and you'll get some incrustation. So in general, sort of message is the smaller size, you have less seed loading, because smaller size give you a large surface area, and really the first principle. So once you have built up this traffic map, and then you can rely on just using the right combination of seed and get crystallizations and operation as long as you wish. So we NiTech, obviously continuous crystallization is one of the key technology, and we have worked with different companies, over 40 fine chemicals, and over 25 APIs, and also there's some compound we have it done there. So really to just the takeaway message, really say continuous crystallization, actually what you want is a consistent environment, therefore give you consistent crystal property at all scale. And this can also reduce a lot of parameters, which lot of item tick box of carbon emission and so forth. And so what to do is I'm going to show you a short video of live continuous crystallization. And to do this, and before I do that, I really acknowledge Chemspec invited me to give us a talk. In order for me to do this, I have to stop share and restart share again. So I'm going to do that now. Stop share, and Right. Hopefully you can see this this video here. I just move this to this side, and now I'm going to play it now. Just 2 minutes. This is a CBD, and because you CBD have a high concentration. Just show you. You can see the nucleation, control the nucleation taking place. Called that's it. Really, thank you for listening, and welcome to any questions. Thank you.